A very good morning and a warm welcome to one and all present here. This is Dr. Maheshwari, Head Department of Mathematics. On behalf of Kumuruguru Institutions, Department of Mathematics is happy to invite you all for the sixth day of the International Faculty Development Program on Mathematical Modeling for Data Analytics and Engineering. Modeling is performed at multiple scales using a wide range of techniques. We use a combination of physics-based approaches and the relationship between the empirical structure property and the protein structure modeling that enables us to understand the molecular interaction between the drugs and the cellular membranes. Here's an opportunity for all of us to learn that these observations suggest several psychotic experiences like the loss of familiarity with the world, hypothetically associated with noisy information processing, thus contributing to subjective focusing to natural social stimuli. For today's faculty development program, we have our dear speaker, Dr. Anuj Mubai, who's the Associate Director, Precision Here, Precision Value and Health, Faculty Fellow, Center for Collaborative Studies in Mathematical Biology, Adjunct Faculty, Arizona State University, Scientific Researcher, Global Pervasive Computational Epidemiology Project, Scientific Researcher for Viral Infection Propagation, that is through the Air Travel WIPRA project, etc. Dr. Anuj is also a co-director of Mathematical Theoretical Biology Institute since 2012. He is a very well-experienced health decision analyst and a mathematical modeler with a demonstrated history of working in the research and the healthcare industry. Skilled in computational modeling and stochastic process, dynamical systems, and data analytical methods, he is also strong in his research as data professional with a PhD focused in applied mathematics for the life and social sciences. He has been an investigator on several federal research grants through the NSF Mathematical Biology and Population and Community Ecology programs and the National Institute of Health and Health Behavior Oncology Research Center. Even before handing over the session to the speaker, there are certain instructions that is to be followed by the participants. If you have any questions during the presentation, please post them into the Q&A tab in your Zoom control panel. It will be answered at the end of the session. The feedback and the e-assessment link will be posted in the chat box on the completion of the speaker's session. Now, I request you to take over the session, sir, and share the mathematical modeling in computation with all of us. Over to you, sir.
I think my screen sharing needs to be enabled. I think I cannot share my screen. Someone has to allow me.
Yes, sir. I'll do that. Please check now, sir.
Yes, it's working. Can you see it?
Yes, sir.
Well, greetings to everyone. Thank you for inviting Dr. Maheshwari, a very warm and kind invitation for me to speak to so many people in India and your institution and many others who are listening to today's talk. I thank you also for giving my introduction, this long introduction. Just to let you know that I have been working on various diseases, infectious diseases from last more than a decade, and build up some backgrounds in how we can address issues that we are facing with the COVID outbreak recently. So I was thinking about what would be the best topic to talk about. And I kind of, I mean, a lot of news that many of you might be hearing is that the models, whether the models work or not work, and what are the challenges. So today I would actually start, many of you are from a different background, so I think I will start with the challenges that we are facing in this uncertainty times, not only from the disease perspective, but from the understanding and from prediction purpose also. So there's always a tug of war between modelers, mathematical modelers, as well as the decision makers who practically follow those results from the modeling world to the real life. And there are a lot of lessons to be learned from what we have been seeing. So before I go further, I want to acknowledge a few of my support. There's one grant that I'm working with. It is called Expedition in Computing, Computational Epidemiology in University of Virginia. I'm part of that. I'm also part of this viral infection propagation through air network group, VIPRA, which is working on various infection propagation through air travel. And then also Intercollegiate Biomathematics Alliance is also very supportive in my research throughout, which is at Illinois State University. So with that, my talk outline will be something on, I would discuss something on why mathematical models have not worked in COVID times, whether it is uncertainty with the data, whether it is measurement problems, or some other issues. And then also I will discuss about challenges in challenges in modeling, how I have captured in my research those challenges. So modeling contact, for examples, or initial rise in cases, for example. So, and then in the very end, I will give a brief outline of how estimations and uncertainties people think about from a modeling. So it is very general talk in terms of how we think about models and how we can use it practically in real life, or whether or not we can use it or not. So I would like to point to a few of the things that have been the words that have been coming into news very often, and these are metaphors, and it captures the different aspects of complex epidemic phenomena. So what word we use in describing some things defines has a different interpretation, basically. And so we cannot be using words left and right, because every has meaning. For example, we are using that COVID is spreading like a wildfires, or we are saying COVID is spreading like in waves, first wave, second waves. There has been other words like shipwrecks, tsunami, and all those things. But what is the difference in this use of word? I mean, the fires, when we talk about fires, is a sudden increase in flares, and it's kind of it takes over the region and then it dies out. Whereas waves is a regular disruption of some things, and or in synchronicity in some sense, that is that has peaks and valleys. But once it is generated, it do not grow exponentially as fires grows usually. So that is the difference, and depends on what we use for defining the phenomena. Because if we define in a different words, we need to be careful how we capture it in the model. So this is a very important point that I wanted to make on this. Well, there has been epidemic models in the field. It is called SEIR epidemic model that has been widely used, and the policymakers depends on heavily on these models. Why? Because the decisions are made for quarantine, when to quarantine, when to isolate, when to re-quarantine, when to open up the lockdown, and so on and so forth. There's a book by Sheridan, very good books, which talks about fortune sellers and big businesses buying and selling predictions. Stress on the very important fact that we make predictions from these models, but we need to compare those predictions with a naive forecast. How much of complexity is important? Whether it is, I mean, we are making these predictions with a complex one. Are we really needed? Are we way off from, or we can use a simple linear model, for example. So, for example, in this book, he used these hurricanes to predict simple line model that he used, Sheridan used, to predict hurricanes, and he was his forecast error was 121 miles away from the real pattern of the hurricane. 20 of those ones, so 18% more higher in is error as compared to US National Hurricane Center models. Whereas US National Hurricane Center models are very complex models, and this guy was using simply a line model, a straight line model, and he was only 18% of the target as compared to the US National Hurricane Center. So the question is, are these naive models predicting better, or we are really need these things? So the question comes to a modeler now: which model to pick? I mean, how much complexity to build upon it? So there are two problems with the naive forecast model, the straight line models that this Shedden used for hurricane prediction. One is the rate of increase is a constant, and basically in the diseases, this rate of increase is never a constant increase. It is all, the rate of increase initially is always an exponential, in because if you have not heard of outbreak, it will grow like very fast in the population, and it's the next one. But not only if you model that thing this with the straight line, there is another issue is that it never comes down, and the real life epidemics actually comes down. It can never grow exponentially. So those are the big issues with the real line, and so therefore they are not the good thing. But they are very good model. The straight lines are very good model early on in an outbreak. Later on, the prediction of that. So it depends on not only how much complexity you have to build in the model, but at what period of time in an outbreak to use which models. That is very. So for example, straight line is a very good model initial early on, for example, in an outbreak. So SIR model, which is very SEIR stand for susceptible, exposed, infected, recovered model, is better in this regard. That what regard it is better? That intervention. So if you see the top right graphs here, on the left graph, there is without interventions. You are not doing it lockdown. You are not doing social interventions. And there is an infectiousness, and there's a peak in infectiousness, which is red curve. But if you do a strict, so what is happening in the left graph is that it is exponentially rising, and then after some time, this red graph is saturating to some level and then dying out eventually. So, but if you, in the right graph, if you have interventions, the susceptible population now starts to decrease slowly in that place. So there is a dark blue regions in the graph, which is showing that infections will stop to rise as soon as you start the interventions, and it comes down. But since you cannot implement interventions forever, because there are other issues associated with it, therefore, as soon as you stop the interventions, the red curve will start to come back, and there will be a second and further waves into it. So this is a simple fact that SEIR type epidemic models can take, but it is more complex than a straight line. So when is to use straight line and when to use complex model becomes a question of a relevant question for a modeler. So, well, before we talk about something more deeper into modeling world, we need to think about why are we doing modeling? Well, we are doing modeling to assist a real life, assist in understanding, assist in some things. So the decision makers, who are the decision makers? Well, government is making policy, so they are the decision makers. They decide on what laws to, whether to close down the city, whether to open up the city, whether to close the schools, and so on and so forth, whether to have who will get the treatment and who will not get the treatment. But their policy questions for decision makers are not about modeling. They are not looking for the modeling. They are looking for a practical applications. So what are the practical applications? So, well, how the scale of policy response to, let's say, COVID can impact not an epidemiological, how can we reduce the number of cases? That is important for them. But not only that, it is also important, there is how much is the economic losses are there? What is the mental health issues are there? So it is not only restricted to number of cases and number of deaths for policymakers, but also other aspects that we as a modeler sometimes don't think. And it is very, very critical to think about these other implications coming of it. And so maybe it is important right now to even incorporate social structure into it, socioeconomic structures into these models. So when to incorporate those things, that becomes very critical. What other things that policymaker assess? For example, how many people will die from a COVID? Not easy question to answer, but because I mean, some case deaths will not be reported, whereas some case deaths will be reported, but these deaths will be due to some other factors or combination of factors. So it is very hard to disentangle which is the cause of the death, for example. So this is one of the questions policymakers are very interested. Will the current healthcare system collapse? And what level, when it will collapse, for example? How many people will be severely ill? Is policy practical in terms of available resources? No country has unlimited resources. Money is an issue, hospital beds is an issue, medical staff is an issue. These things are critical, and we as a modeler sometimes ignore these aspects in modeling an epidemic. And these available resources becomes very. How long will the policy will be sustainable? For example, in India, they closed down the country in few days, and after closing down, they realized the migrants are moving and causing these infection to propagate from one place to other. So they thought of that, yes, because of lockdown, there will be a better chance of controlling the disease. But on the other hand, they did not see, or the models didn't take into account these leakage in the system due to migrant labor. The leakage in the system is very critical, for example, to talk about. So there has been varied levels of policies. For example, Sweden is not doing anything. For example, different level of social distancing, precision quarantine, such as test. South Korea has done precision quarantine. Full lockdown, China did it in Wuhan, for example. And many countries are doing a combination of these things and not only one of these corners. So in these things, we have to know whether which of these policy will have an impact. We have to try all of these things simultaneously or with different permutation and combination in order to make sense. But decision makers are interested in these aspects. On the other hand, the modelers are interested in very different thing, a different aspect of it. So they are interested in, since risk is not distributed across social structure. For example, in New York, there were people who were dying during the outbreak were of low socioeconomic, people who were living in the low socioeconomic conditions. So socioeconomic conditions were very critical in New York, but it was not the case in other parts of the world, for example, or at least not as much part of the world as other. For example, in Washington states, the epidemic was spreading because of nursing home, not about the socioeconomic status, but nursing home was causing, because there was a nursing home where the old age people were there, were forming the cluster of infection, and there the infection were propagating. So different social structure causes different questions for the model. Which aspects of the reality to capture in the model? So this is important for a mathematical model. Once you know the aspects of the reality to capture, what type of math equations better to fit to their goals? For example, one can use differential equation models, or one could use a linear model, line equation of a line. Okay, so both are different type of equations and have a different implications from a prediction and process perspective. Now, we cannot say one is better than other. It depends on a question or the goals in hand that we need a models, for example. How much better are the simple forecast such as linear models? So if if you are making a complex model and you are predicting as good as a linear model, then what is the need of a complex model? The complex model is not doing the good job. You don't really need those ones. So there's, because once you make the model, you need to give the results to the decision makers, and that needs to be as simple as possible. Okay. So this is an important aspect of the modeler, to understand that modeler's roles is not just to predict something, but also to communicate with the decision makers. If the disease will become endemic, or will be regular periodic, or will struck suddenly and disappear, for example. So there are many diseases. For example, TB has become endemic. Measles is periodic. And cholera, for example, comes as a suddenly and then disappear for many, many years. So these are the questions that we as a mathematical modelers are more interested in it. Are the observed disease patterns due to the sudden increase in infectivity? So sometimes there in the news nowadays, we are hearing that the pathogen is changing their infectivity. They are probably mutating. In some regions, it is much more infectious than other regions, for example. So that might be changing. Do we have an understanding of that, or do we capture that aspects in the models? Because our prediction cannot be correct otherwise. How are the changes in environmental conditions or policy that is impacting it? Loss of acquired immunity. Well, we used to think that that COVID person, once you get infected, will never get infected. But recent articles or recent informations are founding that that may not be the case. So a person is immune to the disease only for short duration of time, and then can get the infection again, for example. It is a possibility in the COVID. So the information is coming slowly and kind of making it more plausible for these modelers to think about what to incorporate or not. What factors can bring the epidemic to end? Everyone is trying to do that end. But that is a very complex question to answer. But these are some of the questions that we as a mathematical modeler think about, which is very distinct questions than the questions of the decision makers, for example. So let me give some of the ideas is why COVID-19 models have not worked as much as we want to see as a prediction. Not work means that whatever they are projecting is not what we are seeing in the real life in few weeks or few months. So one of the reasons, actually two reasons which are becoming quite critical is the connectivities of the people. So, well, there is a policies coming and people, social distancing policies that government is implementing that is stopping from people to move. So if there is, these diseases are spread by contacts. These are infectious disease. This is infectious disease. It is spread by contacts. And if you change the value of the contacts that is going in the mathematical models, we will not be able to see the correct path. We will not be able to see the right projections are coming out of it. So density of the population is socioeconomic characteristic of it. Many things that are secondary and has a non-linear impact. For example, healthcare system, population density per facility, basically. So that could be causing the secondary impact on the outbreaks, and therefore the prediction is way off, for example. Well, all models rely on the data. Models are not magic, right? They all rely on the data, and there's a huge uncertainty of in the data. For example, number of cases or number of deaths. Number of cases are each day, the definition of the cases or the testing method is changing. So the number of cases that we are saying is may not be correct. In one instance, China all of a sudden added few thousands of deaths in one day, because they changed the definition of the measurement, that the way they were measuring the deaths, for example. So there is also there is a lot of delay in the reporting also, There is error in the reportings, under-reporting, but also there is a delay in the reporting. There is a super spreading event which could be which can change the dynamics of the outbreak. So we are not capturing. In fact, it is believed that COVID-19 is spreading like a is primarily a cause of super spreading event. Well, it is believed that there was a conference in Singapore for 3 days, and one asymptomatic person was there, and that person infected 7 people. Those 7 people went around the globe and started the pandemic, for example. Those 7 people, it is believed. So it could be a super spreading event that is causing this thing, or it could be virus might be mutating. In some cases, it is very deadly. In some cases, it is less deadly, or they are killing younger age group in some places, or it is killing older age group. So those aspects are very, very critical, and that is probably the reason why models have not worked, because we have not captured those aspects. To build a model, actually, human behaviors and cultural issues are very, very, very important. For example, in US, the policy says now you should be wearing mask everywhere. But some people say, okay, but it's our freedom of choice whether we wear or not wear. So, well, that's, if there is some amount of leakage in that, then it will not work. So cultural issues are there, human behavior issues are there, policies are issues are there, and that epidemic model needs to have an evolving parameters in it, which we are not having it in the initial models. And that probably is the reason why models have not worked so far. So one of the China's example is very good, because it is the first country that was exposed, and we can learn many lessons from that the outbreak in terms of what we have to models. So lockdowns appear to work in slowing and spreading. That depends on intensity of the lockdown. So, well, lockdown helped in slowing. We didn't know that in Wuhan, they literally closed down everything in the city. And that helped in the slowing down the COVID outbreak. But there are different countries and different policies, and sometimes the intensity of the lockdown is not as strict as policy. For example, in India, even though we had a very strict lockdown, but migrants still moved from one region to another. Why? Because, and the government was not very strict. They were trying to do their level best, but they were not strict because they knew that if we stop, people will die from hunger. So that was the reason why they kind of have to lessen the intensity of it. Another thing that we learned, not only the lockdown was helpful, but also we learned that it was 40 days was very important, because if you see in this top right graph, around 40 days, the curve is started to level off. This curve is of number of confirmed deaths, basically. And 40 number, the number 40 is kind of a very critical here, that we have seen in many of these outbreaks. In fact, the 40, in 1600, there was a word quarantine used to come from these ships coming to the cities, and they were, when there was a plague was spreading, and they didn't let people come off the ships for 40 days. They let the ship stand in the harbor for 40 days, and they called it as a quarantine days. So they, in those time, epidemiologists of that times typically knew, public health official knew that 40 days is a very critical numbers. And that is what exactly we are seeing even in this current outbreak. So there has to be something about 40 days. Another aspect is basically, if you see this curve, is that this is something similar to a logistic growth curve of models that we use, for example. Will it be a right one to capture, for example? So these are the questions that are relevant to the modelers, and the points why the math COVID-19 models have not worked. Well, also there is, so let me backtrack. So what we have discussed so far is that why is these COVID models are not working, and another thing we talked about is uh, well, the metaphors. We talked about metaphors also. What is the word we are using for defining certain things? Well, few weeks ago, US Vice President Mike Pence, he said, there was no need to fear about the second wave of a coronavirus infection. He wanted to assure the country. And a few days later, Anthony Fauci, it's a very famous, he's a scientific person, director of National Institute of Allergy and Infectious Disease, said something completely different. He said, unfortunately for us, we will still are in the first wave. Okay, so the question comes here, these two, the way these statements are made, people are understanding these outbreaks in a very different ways. The decision makers have to, these are decision makers, and they are portraying these things, and the behaviors of the people are changing accordingly. So two statements, actually those statements are shaping the pandemic, the outbreak. What will be the shape of an outbreak will look like is driven by these statements made by these decision makers, for example, sometimes. So these aspects are very critical and make a huge impact on whether my model will going to predict or not, for example. So important thing here is actually there are other natural and other social forces that is causing the epidemic waves. The question nowadays for a modeler is, if you see the bottom right of the corner, the possible pandemic wave scenarios that we are thinking about is mathematical modelers and thinking that it will be a peaks and valley and regular waves. We may see the scenario ones, like on the top one. We can also see scenario two, a high peak and then literally die out the infection, fall peak. Or we can see a slow bump. What that means is that there will be a high peak and then slowly damping small waves, basically. So there are different things that modelers are thinking to capture, because these ideas let you write down the correct equations for the models. Another aspect that we are talking about is flattening the curve. It's basically for slowing and spreading of the disease. So the language that scientists use, they are metaphoric. The last sentence is very critical. Their metaphors and rhetoric influence how members of the society at large judge and implement scientific knowledge. And that in turn, the implementation of a scientific knowledge impacts the pandemic shape, and that impacts the data for the mathematical model. So it's a cycle that we are talking about here. It's not only, so sometimes we only think about model as an equations and that's it. Well, there is also the statements that are being made that is driving the people's behavior. Then people's behavior in terms is driving the number of cases, and the number of cases in terms it going as an estimates of the parameters, basically. So these things are a cyclical process, and sometimes that is very critical to understand. Well, this is a mathematician, US mathematician, Samuel Carolyn. He says, purpose of model is not to fit data, but to sharpen the question. Actually, one of the questions that we are asking ourselves is basically, what can be the projection? Is that a right question to ask? Is the projection? Well, the question is different actually, and that will get more clearer as I go in further into my presentation. So, well, let's talk about a little bit past. This flattening of the curve is not a new term. It has been there in the literature for some time. And it started to come into understanding around 2006. In 2006, there is drastic something changes. What changed? And it's very important for a modeling perspective, even though I'm talking about very general how models things, but this aspects is very critical. So in 2006, actually, US has few things going on. For example, there were influenza outbreak, a small outbreak in various regions. There was recent 9/11 attack. There was wars in Afghanistan and in Iraq. There was an attack, mailing attacks. The mails were sent with anthrax pores in 2001. There was SARS epidemic, recent SARS epidemic in 2003, 2004. So because of these things, in 2006, United States decided to make a preparedness team. And preparedness team consists of historians and modelers. Well, I think I want to, the reason I'm talking about all these things here is, well, we are working in isolation as a modeler. Whereas modelers needs to be working alongside with epidemiologists. And this should not be a one-time thing that if the COVID outbreak is there, we build a model and then we forget about the team, basically. This team has to be as a department office, just like National Weather Department. Weather department is a mix of computer scientists, it's a mix of climatologists, a mix of ecologists, and that's a department in all the countries. Just like that, there has to be a preparedness team everywhere. And we don't have that preparedness team. And therefore, we are facing problems is why models have not worked for COVID. So in 2006, there was US made a preparedness team, consist of historians and the modelers. And that is the time they decided to do something. They coined the term something called as stockpile and also flattening the curve. That is the team gave this term, flattening the curve and a stockpile. What is stockpile? Well, they started to collect number of vaccines for certain type of an outbreak or number of treatments for smallpox, for example. Suppose a vaccine for smallpox, for example, if there is a terrorist attack of smallpox pathogen leaked in the population, how many we will need for US population vaccine, for example. Okay, so they started to build those stockpiles based on what modelers have shown using the data at that time. And their result was twofolds, actually. One was that it becomes clearer from the models that a wave moves differently from one place to another. The wave is, if one populations, it will behave differently, and the other place, the wave will, because the population characteristics are different. So this was very important that a population characteristics drives the waves, shape of the waves. They also brought this aspect of flattening the curve. And the flattening the curve has three aspects to it. It delayed the peak. So it gives you time to prepare. It also reduces the peak. That reducing the peak lets you capture the not overwhelming the hospital infrastructure. So suppose you have 100 beds, you don't want to cross the number of cases above the 100 beds. And it diminished the overall cases of health impact. That means the area under the curve got reduced. It diminished the number of cases also. So there was three things that was very significant that they learned from those exercises by preparedness team. But it was possible because there was historians, there was many different background individuals that were working together, and they made a department of that, basically. Although later on, it's unfortunate that that department was dissolved, but at that time, there was many things that we learned that we are still using it and understanding this epidemic, for example. Well, what we do as a mathematical modelers in epidemiological modeling, we do two types of analysis. One is called posterior analysis, and other is called prior method. Okay, so let's talk about each one of it. So posterior analysis is starting from an observed data and working backwards to deduce the underlying causes. That means you start with all the data, and then you come backward to explain why is these patterns showing this thing. For example, in New York, the death rates were very high. And the question was, why the death rate were high? Well, they realize when they look at the different regions, the death rate of different regions in New York, then they realize it is the socioeconomic factors that are driving. The poor regions have higher mortality. So poor regions were causing the mortality to increase, unlike in Washington state, where the nursing homes were the clusters of cases were causing the disease. So posterior analysis is helpful from looking at the observed data and coming backward and drawing the conclusion from the models. That is a posterior analysis. A prior method, on the other hand, is you model underlying causes using a differential equation type models. And that has nothing to do with the data. That modeling of underlying causes has nothing to do with the data, and using them to predict, and only using the observed data at the very end for estimating the parameters. So here the data is used at the end, whereas in the posteriori analysis, it is used in the starting. So these are the two ways the modelers thinks and the work in different ways. Well, the second priori method, there are different types of subdivision of priori methods. Well, there are hardcore theoreticians, no data at all. They don't use at all data. They just use it the nonlinear of difference of based on the logical understanding, and they study the models. There is a moderate theoretical modelers who find data after analysis, after their mathematical analysis then they used the data to actually make that if their analysis is making sense on a hypothesis that they started with. And then there is an applied math modelers. One is spend enough time in linking modeler to data. So they use a lot of time in estimating parameters. So they use a distribution of parameter rather than taking one single value of the parameters, basically. And they use many studies and do carry out meta-analysis to do that thing. And then there's a data-driven mathematical. They start with the many trends of the data, and they try to explain the trends. They begin the modeling from the data itself. And then finally is the quantitative model, use a different type of models from a data-driven questions. So quantitative modelers are using many different types of model, not as a single model. Who says that I have to choose an SEIR type model? Well, you need to check. You need to know exactly how many different types. So there are different types of modelers that are existing in the field, but decision makers do not know that thing. Decision makers cannot distinguish between themselves because their skill sets are different. And we as a mathematical modelers know these aspects, but do not kind of distinguish precisely. And therefore there are nowadays COVID-19 modeling is done by everyone there in this list, which is limitations, because hardcore theoretician may not have all those skills for data linking to the model as compared to the quantitative modeler, for example, or model selections. People might not have had a mathematical understanding of model selection, what basis one should model select, for example. So these aspects are very, very critical when we talk about modelers to an epidemiological model. Well, it's unfair to talk about all these things without linking few models in the past that has not worked. There's one model that came into limelight very early on, which was University of Washington Institute of Health Metrics, IHME model. And it was used by White House quite a lot for their policies. Well, it failed, by the way. But what was this model? This was actually statistical machine learning, linear equation type model, basically. It was a linear equation type models. It was only using mortality data. It was not using cases data. Why it was using mortality? Because they thought mortality is a better and less underreported than cases. Okay. Well, what was the issue? Why did this model fail to predict? I mean, they were way off the prediction. And I think White House has stopped using this IHME model anymore. Well, this, first of all, this was based on that linear models, and this was not include the dynamics of the actual spread of the disease. Dynamics is a mechanisms, epidemiological and demographical mechanisms that drives the systems and creates the dynamics in the disease. That was missing from that. Other thing which was it has a huge margin confidence, huge confidence interval in their prediction. So, well, if you're saying that my prediction is that 0 to 100% of the cases will die, well, that's everyone. So the confidence interval is very important here. It's not only the mean value, but the confidence interval is equally important in prediction. And in these models, the confidence intervals is very large, by the way. Second model that came into picture was Imperial College models. It was done by Neil Ferguson and group. He's a very well-known mathematical modeler. And this model was a computational model with multi-agent individual-based models. And it was using different data sets. So it was using public transportation data. It was using it was using census data, and it was creating some kind of stochasticity, and it was not using the real cases data as such that much. But it was using an alternative source of data and estimating the disease dynamics at an individual level and also simulating intervention of it. Well, this model also failed to capture the prediction. Why did it fail? Well, it was very complex. There's huge number of parameters and therefore huge number of uncertainty associated with each one of it. 15,000 lines of codes. And earlier, the code was not even available to other people. So they didn't know what was coming out of it and how is it designed, what assumptions goes into it, was not very clear. It was also not taking into account the age and comorbidities. That was very critical for control for this particular COVID outbreak, because comorbidity turns out to be very significant in high mortality rate in some regions. So comorbidity is like maybe high blood pressures, heart problems, diabetes. These are comorbidities for these diseases. So those things were not there in these models. Okay, but it turns out these are very critical. Age is very important. Age was not there in that thing, for example. So lesson learned or not unlearned in these things are that what did we learn from all these exercises so far? Well, we have learned from sensitive to input parameters. The parameters input, whatever you put in it is very important. Input parameters are, and the results will be sensitive to that. Huge variation in these things will result to the huge variation in the results. Well, we are putting so much emphasis on prediction rather than understanding how outbreak will spread. This is a major point I try to talk in every, most of my presentations, is we are taking too much emphasis from prediction. Well, prediction is very, very difficult. Rather, we can understand some other aspects of how is disease spreading. Well, unlearn and understand what can we do with this model. What can we do with this model? Pairwise comparison of interventions are better. If you use a single model, you can compare two strategies. That is possible. That is not about prediction, by the way. That is about comparisons of strategies and how those strategies are. IHME models were based on a linear assumptions, and these are statistical models. They were giving a huge confidence intervals, by the way. So pairwise comparison in those things were not really truly possible in those type of models. But actually it is possible in the dynamic model pairwise comparison. And that is the purpose of truly a purpose of understanding the outbreak and the mathematical model. Also is important for a dynamic modeler is to test the robustness in the model. If you are unsure of a certain input parameter, how we can use some optimization or minimization of some kind of error functions to see how we can reduce the impact of it and how much we will reduce the impact of that. Questions we can understand, that question we can use to study about COVID, and that will tell you more about outbreak. We need to be open source model. We need to provide the open source of the model. We publish papers. We don't provide actual code of it. And that is important because we will not be able to do everything. And therefore we can learn from other models and code quickly. And for example, Imperial College model was not available to see for a long time until there was a lot of things in the news show us their prediction is not very good. And then they actually had this thing in open source. Also, we want to ensure that we are not talking too much confidently on prediction when data is scarce and unreliable. Well, every day the new information is coming about the data. And just to tell you, for example, earlier we thought the disease has a permanent immunity. We were talking about herd immunity. But now the herd immunity is not possible at all. Because, I should not say not possible at all, but I think herd immunity becomes a difficult question because what studies are finding out that there might be only temporary immunity, not a permanent immunity. So what is the meaning of herd immunity is not clear. Well, okay, so let me go to this is all about background information about models. Let me talk about some epidemics here. SIR models is a very common models that people use in this type of understanding dynamics of the disease outbreak. Well, there are three characteristics where is very important in epidemic models. These are basically divides the population into three compartments: susceptible, infected, recovered. Susceptibles are not infected of the disease. Infected are infectious people, and are recovered from the disease. So in the population, one of the three categories anyone will belong to, for example. So, and then there is a flow between one compartment to another, and that flow decides how the outbreak will look like, basically. And there is a plot of this graph on the right-hand side. So you see susceptible going down with a black color, and infectious having a peak and then going down, and removed class is kind of saturating to some level. Okay, so what we are seeing in this red graph is three different aspects. Initial outbreak starts exponential. It is rising very fast in the red graph and quickly reaches peak, and it kind of saturate. And then it starts to decline. There are three components to this infectious pattern. Okay. Well, real outbreak is not showing that thing. Real outbreak is not showing. What is, for example, in the United States graph, which you are seeing on the right, is showing that this peak is going on forever, it seems like. So there is not a short peak, but it is flattening in some sense. In European Union, on the other hand, it is also not like I class. Because why is it not like I class? Because it has a long tail. It is not ended. It has a long tail. So it is right-tailed graph, a heavier tail that you are observing, and it's not a clear cut. So these models, simple models, need to be modified to capture what is going on practically in the field, basically. And it depends. The important thing in these grovel is the contact frequency, the way the people contact each others and infect others. Here we assume everyone is equally likely to contact everyone else. So it's another word they use it is homogeneous mixing. Natural extension, if we are not seeing what we are observing from these models, so natural extension of these models comes as multi-risk model. So you increase the risk into it. How do you increase the risk? You include different types of groups, maybe age group, maybe epidemiological stages, maybe hospitalization. There might be severe cases versus less severe cases in the hospital. So there might be cases who are asymptomatic, cases who are not asymptomatic. So self-heal, for example. So there are different groups you can involve into it and try to see which one would going to capture something what we are observing in this pattern. For example, in the graph on the top bottom left, United States graph versus European Union, it has a different patterns basically. So, well, what we have learned here is we see the peak in this SIR model, right? But there is more to that. Let's see what is the more to that. Suppose if we have this SIR model, which is on the left side, and then we slowly add some features into it and eventually come out to the feature that you are seeing in the right, what would happen to the implication? So first step, suppose if I add in the SIR model, E compartment, which is incubation period. E is exposed class or incubation class. That means people who are infected but not infectious. They just barely got infection. So susceptible will go to E class. Then suppose if I only add E class, what changes do I observe? The graph is all shown in the right side. What is seeing between SEIR and SIR is adding an exposed class, flatten the curves. It brings the curves down. So it delays the peak and it's widened at the disease basically. Okay. And that is what, but one thing to note here is it does not change the total number of people who will become infected. It does not change that. Total number of I is the area under the curve does not change. But just adding the exposed class, it shift on the right and it flatten it a little bit. Okay. Now suppose if we add temporary immunity, that what the recent study is talking about. Temporary immunity is that you don't, once you are infected, you remain in the recovered compartment for some time, but then you come back to the susceptible class, and this orange curve arrow basically. So is a SIR model with R compartment going to the susceptible class. What happens if you add that? So you are now feeding people back into the susceptible class. In that case, you cannot generate a peak. The disease will become endemic here. In the second graph on the right, you are seeing second graph that you are seeing there are that the disease is going and settling down with a horizontal line. So it is around about 0.3. If you see in the middle picture on the right side, there's 0.3. The violet color graph is settling down to 0.3, but it's a flat line. So it's an endemic situation. That is not what the COVID virus look like right now. Okay, so maybe the COVID, if it is a temporary immunity, then maybe the COVID will become endemic in our population. We don't know at this point, but it is showing this thing, this model features if you add this thing. Well, There is another aspects that you could, now if this temporary immunity from R to S is very small, from temporary immunity from R to S is very, very small, not too much. So that means you stay in the R compartment for long period of time before you become susceptible. Then you see the bottom curve, which is showing second wave, some kind of a second wave. So if the rate of temporary immunity, you are temporary immunity for long period of time, then there is a second possibility of a second wave. But eventually the disease will become endemic. Okay, so this is a beautiful understanding about these simple models, basically. Now, if I add an asymptomatic class, asymptomatic is A class on the top flowchart diagram. A represent asymptomatic is people are getting infected and then people are recovering from the asymptomatic class. In that class, adding in as a results, not in the shape. It doesn't change the shape too much. What it does, it reduces the reproduction number, which is a very important quantity of these models, which tells you whether there will be an outbreak or not, what will be the peak of an outbreak, and so on and so forth. So it changes the expression of an R naught or estimates of an R naught, basically. So what we are seeing is slowly and slowly, when you build on these models, you see how the actual that trends you are observing in the outbreaks is good for you to capture. So the right amount of complexity is coming back and forth from biology or actual understanding of an outbreak, as well as the understanding of the mathematical construct. If you add the disease category, on the other hand, if you add extra compartment with the death compartment from an I class, disease deaths, and then basically what you will see is the recovered compartment is started to slow down. Why? Because now the more infected people are dying now. So initially in an outbreak, I think the best model would have been SIR model. But now we have more information about an outbreak and we can make it more complex. And starting complex model would not be a good model, actually. So starting first few days of the outbreak, probably a linear model would have been the best model. Okay. And as the information about these disease is coming into light, for example, whether a person is immune or not, how long is an infectious period, whether the person is asymptomatic in that and spreading the infection or not. These all information was not available at the starting of the outbreak. And these informations are going in the refinement of the model as the modelers are now started to build on top of these informations. So I want to talk about this study that we are doing in Ecuador, and we are looking at the transmission dynamics of an Ebola and wanted to evaluate certain types of quarantine and isolation in the COVID outbreak in this Ecuador region. So my collaborators here are Carlos Bustamante. He's a student at Arizona State University, and Jordi Ceballos. He's also a student at Arizona State. They both are from Yache Tech University, beautiful, very good university. They are very sharp student. And Cesar Montalvo, he's in University of Virginia, postdoc. And Jeff Suleiman, he's in Precision Here, which is a economic policy organization, and Edwin Michael, who's a parasitologist in University of Notre Dame. So this work is with them, but we use this work to design the initial outbreak. We were using this work to define, when we did not have much information, how we can understand initial outbreak of the Ecuador. Well, we use a simple model of exponential growth models to understand how fast is the epidemic growing. It is actually in the left-hand side, you see dx by dt is equal to lambda xt. And if you solve that thing, it's an exponential solution. And if you take a logarithmic on the each side, you get a linear equations. Linear in ln of xt and time. And you can use this linear equation to estimate the data. So again, it's type of a linear model, although it's an exponential growth of an epidemic that we were trying to model it, and trying to understand what is the rate of growth, which is lambda, trying to estimate what is lambda is from the real data, basically. Well, not all epidemic grows as an exponential. We realize we were seeing different provinces of Ecuador. We were seeing different provinces of Ecuador, and we realized not all epidemic grows exponentially. Well, and then we decided, okay, this model is not perfect for all of those things. So then what we did was we used a generalized exponential model with lambda xt to the power p, and basically p decides whether it is exponential growth is there or not. So p is equal to 0 means that, what is p is equal to 0? It's a line. Xt is equal to lambda t. It's a line. And p is equal to 1 means exponential. So anything between p is equal to 0 and p is equal to 1 gives you polynomial types of growth, whether it is a quadratic growth, whether it is a cubic growth, right? So this model, some outbreak we were seeing was not growing exponentially, but some outbreak was growing basically polynomial growth. And that is very critical. We did not have much information, ideas about epidemic at that period of time. It was first few weeks in an outbreak. So therefore, we were using this simple model to understand how fast the epidemic is growing. Well, later on, we used an kind of very complex model. This work is actually from my other study, where we use a simple idea about SEIR model, how it can be used to find out exponential growth rate, basically. So here, anyway, I will skip this part. This is but this is what we found from there. So exponential growth rate fitting to the, not all cases were showing the exponential growth. First of all, there were only two states that we found that were kind of showing an exponential growth. Other ones are showing, other of the 6 states were showing basically that they were a polynomial growth. But this is just an understanding that I'm trying to give you in that regard. We then make a more complex models, and this is basically taking into account quarantine, there's taking into account hospitalization, taking ICU beds, and so on and so forth, more complex. But we could not have done this work if we would not had a basic understanding of how fast the epidemic is growing in the previous slide. For example, this was very important, how fast an epidemic is growing. So in this model, SEIR is a susceptible, exposed, asymptomatic, infected. D stands for death, C stands for ICU, H stands for hospital, R for recovered. Q4 is an isolation, strict isolation. Q1, Q2, Q3 are asymptomatic individuals that they don't have symptoms, or they are just like a normal people, and so they are quarantined. Q1, Q2, Q3 are the quarantine, basically. And this model actually predicted 2 waves that we are seeing in the right curve. But also on top of it, we built here the resource limitations of the facilities. C0, if you see C0, this is the parameters were time dependent. Couple of parameters were time dependent. That means it was showing as the health capacity goes above it, you cannot have people in the hospital compartment. People cannot go in the hospital compartment. So therefore, there is a resource limitation, and that is what we built in this model. We also built leakage in the system. Suppose the government says strict lockdown, and there are migrant labor movers. So the level of that leakage from the migrant is also built in this model. So the leakage is also built, resource limitation is built, and it was derived from the basic understanding of linear model, basically. Beautiful understanding, and it gives the preparedness for Ecuador And this was done in many different stages of modeling. It was not the first time we built this model. We started with a linear model, then generalized linear models, then a simple SEIR model, then comes out to be this complex model, basically. So it was a step-by-step procedure as more information were getting available from the real world about the COVID outbreak. So this is a model that also we use for Zika, very simple models. And we use this model to estimate, well, how many data points are needed to make, to use an exponential growth model. Well, whether you should use 10 data points, whether you use 20 data points, that was not clear. So we use different types of points and came out with optimal number of points instead. Why? Because we know the outbreak will never always be exponential rise. Eventually, the outbreak will turn over and become reaches peak and kind of comes down. So how many data points from the starting one should take? That's an important thing in exponential. So we did that test here, and we tried to find out what will be the best way to estimate this initial exponential rise. Another thing that was very critical here was how we can go back in that. So, I mean, the cases might be reported in India on a particular day, let's say. But is that the outbreak started on that particular day? No, not necessarily, because the cases might be, the outbreak might be there from few days, but then only the cases get reported very late in it. So we predicted using this model, when was the first case that was reported, basically. So there were multiple aspects that we talked about in this type of study. Well, all these things are very critical to how you measure contacts. It is very important. These things we are modeling it, but the contacts, the how you measure it, how you capture it, that describes the features coming out of your model. For example, SEIR model is simply a homogeneous model. But if you incorporate age or incorporate quarantine, isolation, hospitalization, that becomes more heterogeneous in nature. Okay, so then you need to know how each of these compartments are interacting with each other. So that contact rates needs to be defined now. So think about it. Now, what is contact? Well, is it a physical contact? When you touch someone, then only there is a contact, like handshaking or kissing or hugging someone. Is that a contact? Or it is you are standing 6 feet away, and that is a contact. For example, in Ebola, it was a body fluid that was a reason for a contact. Whereas in COVID-19, 6 feet distance, you can be infected if you are not wearing mask, for example. Okay, so non-physical is a contact in this case. So the measurement is very difficult to do that, whether the frequency is daily, weekly, how you are measuring it, whether it is per day you are talking about, whether weekly, because today's contacts are not same as my tomorrow's contacts. Okay. Now, also it is important is the duration of the contacts, whether it is 5 minutes standing close to a person, whether it is 15 minutes contact, whether it is 4 hours. So that duration also. So these things goes in the estimates of the contacts in order to make a plausible understanding from these models. Not only that, these contacts are changing over time because of the policies. And therefore, we are using these SIR model and predicting it will not be correct unless we thoroughly understand how we can measure contacts and how do we capture it in the model in better way. So there are 2 ways you can model is directly take contacts from the data. So suppose you have age group. So suppose you say children who are 18 years younger versus adults, young ones who are 18 to 30 years old, 30 to 60 years, how they are mixing within the group or within each other. You can take directly a data of contacts, the way you define it, physical or non-physical way. And then you use those numbers in the model, or you can model the contacts also. You can model it by saying, okay, I assume same contacts with everyone, but contacts will change based on number of people in that group. For example, age group, if I take young and adults, and the number of contacts in young is proportional to number of people in the young, and number of adults contacts will be proportional to number of adults in the so that is a modeling you are doing. Now you are saying C is not constant everywhere and coming from directly from the data, but it is coming as a function of number of people in that subgroup, basically. So that is called as a proportionate mixing, basically. But there are other ways you can model also. There are preferential mixing. You may be, for example, children, school-going children usually mix with two types of adults, with parents and with teachers. They don't mix with the general adults, usually, school-going children. So they are preferential mixing there. They are preferred to teachers and they are preferred to parents and not preferred to other adults, adults who are working in other businesses, for example. So that's a preferential mixing, basically. Now, how do we model, capture this data? Well, this is a very rigorous procedure. This is a very, very rigorous procedures. You need to ask questions to these guys and capture these physical contacts. Was this physical contact? How long you were there? Did you touch? There are different questions, and then you quantify that thing. Where did this happen? Did it happen in the workplace? Whether it happened in the college? Whether it has happened during travel? And so how often happens? It is every day, once a week, twice a week. So these all aspects make important characteristics about measuring the contact through network. So anyway, so look at the complexity involved in these measurement of contacts and the complexity in modeling the contacts. And we are not paying attention in the modeling world on these contacts. And we expect to have a proper projection, proper prediction. My answer is no. That is one reason why we are failing to capture the projection or prediction. But anyway, so this is a general idea. Well, we build another studies using effective contacts in infection transmission models. So for example, these are individual based models, for example, and each individuals are categorized either into susceptible or infected. And then every time units, each susceptible person has certain number of infected people around that susceptible. And so the question is, how do you capture this thing? So we use this formula to capture the number of people who will be infected over time. And this important aspect was M here. M is average number of contacts here, total number of contacts, which is changing over time. So every time a step, the contacts are changing. So this is very involved model at an individual level, but taking into account various things, like it is taking into account M and P. P is one aspect is number of infected people, but we assume in this model also that each infected peoples is spreading virus in a different rate, not the same rate they are infecting. So some are infecting more and some are infecting less. So this is captured by this way here. And Dr. Maheshwari, please do let me know if I have to stop. I think I'm going almost about close to my...
We can have for the next 5 to 7 minutes. Yeah.
Okay, sure. So the question comes is, how do you capture this PC? PC is the infectivity of a person. How many viruses a person is spreading? So we use this data from Center for Disease Control, which is saying this is a viral load in each of the individuals. So as the age of infections are progressing, how many cases, how many viruses are generated in the person, in an average person, which is different for Ebola versus in SARS. And this distribution goes in the PC, for example. So the complexity was but the contact was very critical in this part of studies. Well, I want to end, I think, with some of these points that so we need additional careful epidemiological understanding to understand how the COVID pathogen is spreading, and the different modes of transmission. For example, the maybe the surfaces are spreading, so maybe asymptomatic people are spreading more in COVID, it is known, than symptomatic people, for example. And also understanding what are the areas of uncertainties in these ones, and modelers needs to know those things. And of course, without knowing the mechanism, it is very difficult to predict the results. So I hope I have made a point here to explain the challenges in it and why the models have not worked, and what are the things that are going into it that are more complex in nature than what we as a modeler sometimes believe or capture. And with that, let me give a final picture to you guys. And this final picture shows you the complexity in the modeling. And then you will see, so complexity comes from parameter sensitivity, that you are not sure of the parameters that are going in it, precise estimates of it. So that gives the parameter sensitivity. Another complexity comes from observational sensitivity. That means whether your model is fit for the data, that given data, or there is some other model you have to use, whether this observation has what type of observation is the data, basically. So what type of errors are there in the data, and if your model can capture it. And third is structural sensitivity, model selection. That means which model to choose, whether it is a linear model to choose, whether it is a dynamics model to choose. Those are very critical. And finally is the outcome sensitivities, is the how confident we are in the predictions, how much uncertainty we are showing, and whether we are able to show the uncertainty in a right way or not. As IHME models were missing, their confidence interval were too high to show any predictability. So mathematical modeler has to think in all those four places, and not only into the just modeling some things, basically. So with that, I will stop here, and I hope I have made a point of many different angles of definitions of challenges of understanding and depthness of understanding, and implications from the model. So thank you very much for having me and hearing patiently. I hope it was interesting to some of you.
Thank you so much, sir, for this excellent talk on the different mathematical concepts with respect to modeling techniques that each one of the modelers look for. And you had also given a brief insight on the present COVID-19 modeling, and that is one of the greatest challenge which all of us are facing in today's world. So, sir, shall we go on for the Q&A session, sir? Some of the questions they've asked.
Thank you.
So we shall just look into that. Many states in India are claiming there is no community spread. How to mathematically determine or confirm from the data if it's a community spread or not?
Well, that it is whether there is a community spread. Now, there is one thing we need to realize as a modeler is there are some things that is not our cup of tea. What that means is there is two different fields that we know about. There is an epidemiologist and there is a mathematical modeler. So there are some questions it is meant for epidemiologists to measure. There are some questions that mathematical modelers can measure. So for example, whether there is a community spread or not is an epidemiologist question. It is not a question of a mathematical modeler. So I think the testing or where to focus our attention to find clusters, or where to go in the community to find whether it is a community spread or not, how to properly sample the population to find out whether the community spread is there or not, or whether it is only a super spreading or clustering event happening. That is a question of an epidemiologist, not of the question of a mathematical modeler. So I think what we are asking ourselves is if there is heterogeneity in certain population, heterogeneities of infection process, then how the patterns of the infection will change. That is a mathematical modular question. Okay, I hope I've given some. And this is something that we need to understand is like, what is an aspect that epidemiologist or public health aspect of people will going to answer, and what is the aspects that we as a mathematical modeler will going to answer. And then there are decision makers who are also taking decisions based on it, on these three set of group of people. And so if we cannot, because some things we ask in our news, something we see in the news is not really a concern of as a modeler. So I'm talking from a mathematical modeler perspective, and that is, and so it's very difficult for me to say whether in India it is a community spread or not. This is something has to come from an epidemiologist. Thank you.
Sir, shall we go for one more question, sir?
Sure.
Now, which one is consistent, either imperial model or Oxford model? And does this consistency is based on the different mathematical modeling approaches or the different key parameters?
Well, up till now, none of the model has been able to predict in a precise way the patterns that are being observed in various places. Well, what my talk was about was why it has not able to, and the reason it was not able to build it is because they are not taking their contact as a function of policies. They are taking they not only time dependent it should be contacts, but also it should be policy dependent behavior. There's two aspects going in the contacts. One aspect is how the government takes the policies, and second is how people change their behavior. Those two things goes into the contacts in a proper way. Now we don't understand how exactly it goes. So their confidence intervals sometimes capture the patterns, sometimes do not capture the patterns. And so actually most of the time they are unable to capture. Now, again, as the data is getting more and more accurate and more understanding about COVID-19, we are getting to know, we are now able to get the confidence bound more finer, more less confidence interval that we are getting. So thank you.
I think all participants must have got their questions answered. And moving back to, sir, thank you so much on behalf of Kumuruguru Institutions. We thank you, sir, for spending your time and sharing on the current topic of mathematical modeling for infectious disease with all the participants. And I believe that the participants must have also got a thorough insight of the information that has been provided by you with respect to the purpose of models is not to fit the data, but to sharpen the questions. And you've also discussed on how the contact measure is very important in the field of modeling. And we thank you, sir, for the time spent on answering each of the questions that was put forward to you. We thank you for your kind gesture and hoping to see you again in our coming days, sir. I believe that all the participants also have thoroughly enjoyed your session. Thank you once again, sir. Thank you so much. Very kind of you, sir. Anything from your side that you would like to share with us, sir?
Sure. I would like to say, first of all, it has been an honor and privilege to talk and thank you for your invitation, Dr. Maheshwari, and all the people who were involved behind the scenes to arrange my talk there. And I will be happy to interact further on any of the questions or follow up with the questions later on, or any kind of research studies also to talk about. Hopefully we will get more interactions in near future.
Yes, sir. Even I'm looking forward for that only, sir. Me and
Sure.
all the participants from our side also are looking for the same. And hoping to see you again, sir. Thank you so much. And
Yes.
I also thank all the participants for looking into today's session, and hope all of you are also benefited from this great session. And I request all the participants to kindly fill in your feedback link that has been provided in the chat box, and then log out the session. And that's all from our side. This is Maheshwari signing off from Kumuruguru Institutions. Thank you all. And tomorrow's session, for your kind information, is at 3:30. The new link will be sent by today evening. All the participants. Thank you all.
Thank you, Dr. Maheshwari. Take care.
Thank you, sir. Thank you, sir.